Now we'd like to study the Kepler's second law. Kepler's second law said the radius vector from the Sun to a planet sweeps out equal areas in equal period of times. So Kepler's law said this areas is always constant, increase. So if you use the equation, ds over dt is equal to the constant. So first of all, we'd like to find out the area of an ellipse. So we consider the ellipse. This is a, this is square root 1 minus e square a. This is minus a. This is minus 1 over e square a. So we'd like to discover the areas in these regions. So in this type of the situation, it's better to consider the circles with radius of a. Then areas of this radius of r is a pi a squares. Then this ellipse is compressed in the y-axis by a factor of square root 1 minus e squares. Then you can easily imagine the areas of the ellipse can be calculated. Pi a square times factor of the compression 1 minus e squares. This is the area of an ellipse. Okay, then with remembering these factors, let's move to the next slide. Constant k. We'd like to discover the constant k. In the Kepler's second law. Kepler's second law said ds dt equal k. We'd like to express the k. We integrate both sides of this equation. So this means ds dt equal integral k dt 0 to the order 1 rotation. So in the left hand side, k is constant. So it's quite easy to find that this is kt. Capital T is a period. And the left hand side, dt is cancelled out. So ds, integral ds, it becomes areas of the ellipse. So we have already discovered this corresponds to the pi a squares square root 1 minus e squares. This corresponds to the area of an ellipse. Then this is equal to kt. Then you can find this relation. Then k is expressed by dividing by t. You have an expression for the k. Okay. Then we have already find out the k. But now we'd like to introduce the new terms, or mean angular velocities. Angular velocity is angle divided by times. So mean means 2 pi is a 0 to the 2 pi. 2 pi radians is divided by the period. That's the mean angular velocities. Instead of k, sometimes it might be better to use the n. So by substitute here and then remove the k to find out the expression for the Kepler's second law. Another expression for the Kepler's second law. We'd like to express the areas of these areas. This area can be approximated by the area of the triangles. This triangle. Then height of the triangles. This angle is a DF. So if you consider this triangle, you could consider height is expressed R sine DF. So this distance times height. This is a distance R plus dr times R sine df. This is height. Times 1 over 2 give the areas. This is correspond the areas. And then dr, df is a very small. So we would like to ignore these terms. And the sine df. So if we consider the small value of the df, sine df over df is nearly equal to the 1s. So we use this relation. So sine df becomes df. So areas of this region is expressed 1 over 2 r squared df. So Kepler's second law, ds, can be expressed these equations. 1 over 2 r squared df. So now we have a final formulas for the Kepler's second laws. Kepler's second law can be expressed 1 over 2 na square root 1 over e squares, or you could write on the 1 over 2 r square df dt. This is the end of this session.